recently received a 4 kilogram box of chocolate. So this one, it's like full. It's like this small box. It's like really heavy. It's like what was it? It's like what was in it? It's like, what was in it when we opened it? It's almost like something metallic because it's a really heavy box. It was like this big, and it was like this high. It was like 4 kilograms. Yeah, 8 pounds of chocolate, and we were just giving it away because I'm not eating all this chocolate. It's entirely full of chocolate bars. Oh, thank you. Next semester, can we have a game night with Friday night game night with Chen? Yeah, we can just any game really. We just go and clock in on Steam and just play some games. Next semester, you seem to have actually a lot more time than I thought you did. You seem to have a lot of time. You have time to go, but we get the time to watch JoJo's. Chen's, Chen's Bizarre Adventure. Excellent time management skills, I say.
All right, let's start. Once again, on the screen here, you see the final exam time and location. Please make sure you go to the right place at the right time. Same place as usual, Hall of Music, same seating block. As usual, make sure you know where to go, your section number, and all that good stuff. Okay? Also, please also keep in mind that there are SI sessions. And if you're looking for more help, make sure you look up the schedule on purdue.edu/SI. I sent by email that the one on Sunday, this coming Sunday, is canceled. So there's not going to be one this Sunday, but all the other ones should be being held as scheduled. All right, let's continue with the practice problems. Last time we ended at number 12, right? I think we stopped at number 12. Let's continue. Number 13. Here we got a related rates problem. Water is withdrawn from a conical reservoir. So there's our famous or infamous conical tank, 8 feet in diameter. And 10 feet deep, vertex down. And then it says that water is leaving this tank at 5 cubic feet per minute. We want to know how fast is the water level falling when the depth of the water in the reservoir is 5 feet. So let's say this is the amount of water inside the tank, and the depth from the vertex is h. We want to find how fast it is falling. dH/dt, the rate of change of the height, the h, the depth, at the moment when h is 5. Okay, as usual with all of these related rates problem, this part you want to ignore that until after a derivative. The water level is changing at all times. It's never a constant. We're interested in something at the moment when it is exactly equal to 5, but that's just one instance in time, right? So you got to set up the problem first, get your derivative set up, then you worry about this when something happens. The problem here tells us the volume of the tank of a cone is 1/3 pi r squared h, and r is the radius of the water's surface. Okay, so you got, of course, the water inside the cone is the little cone, and the volume there is given by this equation. The first thing we notice here is we're told that water is leaking. We are losing the volume of water inside the tank. So that means the rate of change of the volume is a negative number, and it's leaving at 5 cubic feet. Negative because water is leaking out. So the volume is decreasing. We're losing that quantity V. Okay, now you look at this problem right here. Look at the volume equation. We have two things that are changing at all times. We have R and we have H. We want to reduce to just one variable. It's not easy to deal with two constantly changing things. We want to reduce down to R or H. Now, which one you reduce, in general, really doesn't matter. However, we are looking for more information about H. That means we don't want R to stay in the equation. We want more information about H. We also know a little bit more about H. We know nothing about R, but we know something about H. We also want to know more about H. So we want to get rid of that r from that equation. Let's take advantage of the fact that if you look at the tank from the side, we see a triangle. Diameter is 8. That means the radius at the top is equal to 4. And then the water inside the tank has a depth of h, radius of r. If you chop that in half, then we can use similar triangles to relate r and h. We know these two triangles, the shaded one and the big one, are similar. They share the angles. So that means the ratio of their sides will be the same. 4/10 must be equal to r over h at all times. Back to the last page, we don't want r in that equation. So we solve for r. Four over 10 is 2 over 5. So we see that r is equal to 2 over 5h. Now we can take that into the expression for the volume of water in the tank. 1/3 pi r times h. And that's the same as 1/3 pi times 4/25 h squared, one more h cubed. So clean this up just a little bit. We get 4/75 pi h cubed. Okay, and now we can deal with what we want to find. We have v is equal to this depending on just on h. Now we take the derivative with respect to time. Left-hand side dv dt. On the right-hand side, 4/75 pi is a constant. The only thing that's changing on the right-hand side is h. So its derivative would be 3h cubed. By the chain rule, we need to attach dh dt because h is also an implicit function of t. We know how much water we're losing. We're losing 5 cubic feet per minute. So the rate of change of volume is -5. On the right-hand side, we got a lot of things going on here. Let's multiply the 3 and the 4. Now we can deal with the moment when h is equal to 5. Okay? The problem said, want to find dh dt at the moment when h is equal to 5. After we've taken the derivative, we can put in that number. And now the only thing we don't know is dh dt. Let's find out what it is. Yeah, the numbers are kind of messy, but we can deal with it. So what do we got? We got, okay, that's annoying. So -5 times 75. So I'm multiplying this over, divided by 12. Pi also comes down here. 25 comes down here. So what do we get? We get, that goes away, that's a 5. That's a 12, I think. Is that right? $15, sorry. Okay, so what do we get? We get negative 15 over 12 pi, is that right? These numbers are annoying. What did I do wrong? It's probably screwed up here. I know it. It's good? Really? Oh, wow. Huh? Okay, yeah, that's right. Minus 5 over 4 pi. There we go. That would be feet per minute. So that means it's decreasing at a rate of 5 over 4 pi feet per minute. All right, any question on this one? Okay, so that's a very typical related rates kind of problem. Almost always there's some kind of triangle in the related rates problem. Almost always. The other variations we've seen are things like the man walking away from the light, shadow on the wall, something, something, shadow on the ground, a kite flying horizontally, the angle and all that. They're all variations of the same thing. There's always a triangle somewhere. With triangles, you can do a lot of things. All right, so that's 13. Moving on to 14. A rectangle is inscribed in the upper half of the circle, x squared plus y squared is equal to a squared. Calculate the area of the largest such rectangle. That's a circle of radius a. A is a constant here, treated as a constant. And inside the rectangle, we would like to fit, inside the upper circle, we would like to inscribe a rectangle. Remember, inscribe means you want something to fit just underneath it. It's touching whatever is bounding above, in this case a circle, but not over the circle. We are looking for the maximum area of the inscribed rectangle. Okay, so first thing we need to do here is to notice that this edge, this little corner here, can stay on the circle and move around on the circle, but not go over. And it cannot go under either. So let's call that point x comma y, which means half of the width of the length of the rectangle must be x. Right? This much here, that's our x coordinate. And the height of that rectangle, our y coordinate of the point, must be y. And if we call the area capital A of the rectangle, then the area would be the length times the width. Half of the length is x, the whole length is 2x. And just like last time, because we're going to go ahead and differentiate this next and find the critical numbers and all that stuff. But we don't want to do that before we get rid of one variable. It doesn't matter in principle which one you get rid of, but typically we get rid of y, and we can do the same thing here. X and y are the coordinates of the point that's on the circle. So they must obey the circle equation, which means the circle equation tells me what x and y, how x and y have to be related. Okay, so from the circle equation, I see y is equal to the radical of a squared minus x squared. This goes in here for that y. And also, why the circle equation? Because the problem says so. Yeah, so that's a good point. You got to read the problem to tell. It'll tell you what shape you're dealing with. It could be a line. It could be a hyperbola of some sort. Whatever the equation that's given to you, that's the equation you work with. Okay. Also notice here that we actually have a bound on what x can be. X is half the length of the rectangle. It can be no smaller than 0. It can also be no bigger than a. So this makes this a closed interval problem. It's equivalent to finding an absolute max and min of certain quantity. Okay, let's take the derivative. Product rule first. Derivative of the second. Plus the second. Remember, a is a constant times derivative of the first. Make it equal to 0 as usual. So things here are a little bit messy here. Be very careful. 2 and 1/2 can go away, and then we're left with a negative 2x squared over that thing under a radical. Over here we get that. Okay, 2 and 1/2 go away. X and x squared minus 2 on the top. This one's got a negative 1/2 as a power. I brought it down here. Okay, then I can solve. We're looking for x, of course. I can take that negative 2x squared over radical a squared minus a squared to the right-hand side, make it a positive. Then I can cross multiply. I can multiply this over and divide it by 2. Okay, these multiply together, the radical goes away. Right-hand side, the 2's cancel, we get x squared. So we end up getting 2x squared is equal to a squared, which means x squared is equal to a squared over 2. So x must be equal to a over radical 2. Actually, also negative a over radical 2, but that one we're going to automatically reject. Because we know from the problem set up here, a cannot be negative, and x cannot be negative, and a is understood to be a positive number. All right, so that's our critical number. Now we check the area at the endpoints of the interval. A at x equal to 0, A at a critical number, A at the right endpoint. It's a closed interval problem, so it's equivalent to finding absolute max and min. Yeah. Right. Yeah, exactly. You would know from the setup of the problem. Absolutely. Just by looking at the problem or looking at the A equation, either way, you can know automatically the two endpoints will be 0. So therefore, whatever this number is, that's the maximum area. All right, so it's 2x times a squared minus x squared 1/2. Right, that's our A equation. Okay, so what do we get? We get 2 times x times a squared minus that thing squared to the 1/2, and we get very annoying stuff. Radical 2a, this is a squared over 2 under a radical. So that's radical 2a times a over radical 2. Those go away, so a squared, is that right? Yeah, looks right. Okay, so focus on how this kind of problem is done. Inscription under a certain curve. Pay attention to the setup, finding the critical number, and then finding the highest thing. Questions? Nope? Good. All right, so those two took a while because, they're understandably more complicated. Next one. This one is shorter. Given that f of x is differentiable for all x, we're also told that f of 2 is equal to 4, and f of 7 is equal to 10. Then the mean value theorem states that there is a number c such that then 5 things to choose from. So first thing first, let's review the mean value theorem. Okay, so the mean value theorem says, remember, for a differentiable and continuous function, what it says is that there is at least one place between the two endpoints where the tangent line slope will be equal to the secant line slope. So it says that there is at least one C, where C is between A and B, such that f prime of C, the tangent line slope at C, is equal to the secant line slope. All right, so that's the mean value theorem. It contains Rolle's theorem. Rolle's theorem says it's the same thing, except we require f of b and f of a to be the same thing. It is automatically contained within the mean value theorem. So knowing that will take care of any problem that Rolle's theorem is involved in. For here, now it seems pretty clear, right? We know that there is at least a C where C is between 2 and 7. Such that f prime of C is equal to the secant line slope. F of 7 minus f of 2 over 7 minus 2. And so that means 10 minus 4 over 7 minus 2, which is 5 over 5, and that's 1. 6 over 5, of course, yes. 6 over 5. Okay, and then you look at the 5 choices. There's one of them that says that. Looks like A, is that right? A? All right, but that's something you gotta know. If you don't know that, then this problem is it doesn't, because we can't find out because we don't know what F looks like. Always says that we can find at least one place where this is true. There could be multiple, but until we know what F looks like, we can't find out where that is. All right, continue. Number 16. Suppose that the mass of a radioactive substance decays from 18 grams to 2 grams in 2 days. $18 grams to 2 grams in 2 days. How long will it take for 12 grams of this substance to decay to 4? This is an exponential growth and decay problem. And for that, there are two key equations you need to know. One of them says that the rate of change of that quantity y is proportional to its current size. So constant times whatever y is equal to. The other one, the equivalent equation, is y of any time t is y at the initial time times e to the kt. And there's a version of that for Newton's law of cooling. If Newton's law of cooling were to be on the exam, we will give you the equation, Newton's law of cooling equation. Okay, but otherwise, this is the kind of thing you need to know. So this is what we got here. The rate of change is equivalent to some constant times its size, and then the following equation. The key in this problem is to find out k. Once you know k, everything else is known. Okay, so let's look at the first part of this thing here. I'm just rewriting that equation here. I initially started with 18. At the future time, I end up with 2. So that's my future amount on the left. Y of 0 at the initial time, that's my 18. We don't know K, but I know this took 2 days. All right, so 2 days later, my 18 grams of stuff decayed to 2 grams of the same thing. Here, I need to find K. Divided by 18. 1 over 9 is e to the 2k. Take natural log. So k is 1 over 2 times natural log of 1 over 9. Or equivalently, natural log of 1 over 9 to the power of 1/2. Now I know K, I can work with this equation a little more. Future amount is still equal to the initial amount times e to the kt. I know K now. Okay? We can rewrite this a little bit. We've done this a couple times before. The part inside the green brackets, e to the natural log of blah. Remember, that just reduces to blah. E to the natural log of 1 over 9 to the 1/2 reduces to simply 1 over 9 to the power of 1/2. That thing is still raised to the power of t. Simplify a little bit. We can rewrite it as y at the initial time times 1 over 9 raised to the power of t over 2. Okay, now with this equation we can answer the question. How long does it take for 12 grams to decay to 4? My initial is 12, my future is 4. So in this equation here, future on the left, initial on the right, divided by 12. And we can do a bunch of things here. We could say 1 over 3 is equal to 1 over 3 squared raised to the power of t over 2, because I know 1 over 9 is 1 over 3 squared. So I replace the 1 over 9 with 1 over 3 squared. And that makes the right-hand side simply 1 over 3 squared to the power of t over 2. That makes it 1 over 3 to the power of just t. 2 times t over 2 is 1t. And therefore, this means t is equal to 1. B, yeah. This thing? Yeah, sure. Yeah, you can do that. And in the end, oh, then we would skip that step here. Probably. Well, knowing what we know, it would help. Because I ended up doing the same thing here, right? Yeah, you're right. Yeah, so what he's saying is that we could have just started with ln of 1/3 here and work with the rest of that. Yeah, that would help out somewhat. Okay, other questions? make sure you look over the exponential growth and decay homework problems. Also take a look at those Newton cooling problems. Like I said, we will give you the equation if there is to be one, but at least review how you would solve a Newton problem. All my pens are dying. So green then. 17, which of the following is/are true about a function g of x is equal to 4x cubed minus 3x to the fourth? So it's dealing with increasing and decreasing. Oh, I'll write those down. First one says g is decreasing for x is greater than 1. 2 says g has relative extreme value at 0, 0. And statement number 3 says g is concave up for all negative x. All right, so let's find 1 and 2 can be knocked out at the same time. Let's take the first derivative. We're looking for the critical numbers. So 12x squared minus 12x cubed is equal to 0. Take out the 12x squared. And we get 12x squared times the quantity of 1 minus x is equal to 0. This tells us that x is equal to 0 and x is equal to 1. Now let's check out the sign of g prime. Once we know that, we can see if the first one is true. And once we know all the signs, we also know if the second one is true. Okay, so let's see. If I want to choose a negative x value, put into g, I can put into either one of these. The second one is more useful because this one is automatically positive. Only that part will determine the sign. If I choose a negative x, negative 10 for example, then I have 1 minus minus 10, that's a positive number. Positive increasing. If I choose between 0 and 1, say 1/2. 1 minus 1/2, that's also positive. If I choose a 2, that's a negative. Okay, so 1 is true. 2, there's no sign change here, so there cannot be any relative max or min. 2 is false. To find out if 3 is true, we do the same thing with the second derivative. G double prime. 24x minus 36x squared equal to 0. Take out the 12x. This tells me that x is equal to 0, or x is equal to 2 over 3. Repeat the same thing with the second derivative this time. And really, all I care about is what happens with negative x. So let's just do that. If I choose a negative number for x, then this will be negative. this will be positive. So overall would be negative. Negative means concave down, right? So concave up for all negative x, that's clearly false. Any question with this one? All right, good. Moving on, number 18. Find where the function 2 over radical 1 plus x squared is increasing. That doesn't look so bad. Yeah, we kind of did the same thing on the last problem, but we had a simpler function last time. This one is not so bad. If you rewrite the function as 2 times 1 plus x squared to the negative 1/2, then its derivative is pretty easy to find. We get negative 1 plus x squared to the negative 3 over 2. Ah, 2x. Ah. What did I say about chain rule? Oh man, that's not good. Okay, so what is it? 2 over radical 1 plus x squared. We're looking for increasing intervals. 1 plus x squared to the minus 1/2. Take the derivative properly this time. Negative 1 plus x squared to the negative 3 over 2 times 2x. Chain rule, right? 2x. So that's equivalent to negative 2x over 1 plus x squared to the 3 over 2. Critical numbers. Clearly, f prime is 0 when x is equal to 0. The numerator is 0. Don't forget that sometimes you have to worry about when the first and second derivative are undefined, when you find your critical numbers and where things are equal to 0. Here, however, it will never happen because we can't make 1 plus x squared equal to 0 at all as long as we stick with real x. Two positive quantities can never add up to 0. It's impossible. So the only critical number we have is 0. Now we draw the chart. At 0, f prime is 0. Now we check left and right. Downstairs is always positive. That's a positive quantity, square root of that, and then cube that. So let's see. If we choose, I don't know, minus 1 maybe. And so what do we get? We get positive here. We choose 1, this will be negative. Increasing, therefore, it will be for negative values of x. Right. Okay, questions on this one? Okay, I think we can do the next one too, and that's actually pretty good because then when we start again on Friday, we'll be looking at integrals. So let's knock out the next one. And also on Friday, I'm going to do a Newton's law, Newton's cooling law problem for you, just so I keep talking about you to review, telling you to review it. I'll do one on Friday. Okay. Let's see. Number 19, we are given f prime. The function has a relative, essentially, where are the relative max and min? All the 5 choices deal with where they are. So that's all we need to do, find out where they are. And this is actually pretty simple because you got the derivative already. You make this equal to 0, that means each of these 3 parts is equal to 0. So this whole thing will be 0. You can see when the first part is 0, which happens at x is equal to 1. When the second part is 0, which happens at x is equal to minus 2. And the last part equal to 0, which happens at x is equal to 5. Draw the chart again, the line. Right, you really don't want to use the second derivative test here. You don't want to differentiate this. You don't have to. Don't do it. It's not a very easy function to deal with. We'll just look for the sign change. 0, 0, 0. The first quantity is always positive. That's not going to determine anything. Check the last 2. If I choose negative 3, that's a negative, that's a negative. So overall positive. What am I missing? No. 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 No, you're talking about this. This is x plus 1 and minus 1. So no. Okay, we're here. Again, we'll check the sign here. That's increasing here. Now check between minus 2 and 1, 0. Positive, negative, decreasing. 4, positive, negative, decreasing. 10, positive, positive, increasing. Plus to minus, we have a relative max. No sign change, that's nothing. Minus to plus, we have a relative min. Maximum at x is equal to minus 2. Minimum at x is equal to 5. That does not mean, remember, that relative max is minus 2. It just means where it is at minus 2. Without knowing what the function looks like, we don't know what the actual maximum is. We only know where it is. Okay, so we're done with I think what we got left are mostly integrals with, looks like L'Hopital's rule and other stuff. So we'll continue that on Friday, and I'll do a Newton's law of cooling problem too. That's it. See you Friday.
Thank you so much.